Okay, here we are with the last of the new material. This is actually something that I learned by watching a sitcom way back in sometime in the 80s. So there is a formula here. I don't know, it was weird. Sitcoms weren't usually very informative, but this one was. Uh, these infinite ones are pretty easy to solve for, actually. So find the sum S of n of the first n terms of this sequence. And these are geometric. So we can use this formula up here. This one has a dot, 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 so it goes on forever. Here is the way that I do it, and I kind of usually end up ignoring this formula up here. So what I'm going to do is I'm going to say that I don't know what this answer is. So I'm going to say that it's equal to x. What is that common ratio, though? To go from 2 to 6, I multiply by 3, and to get that in here, I divide by 5. So I must have 3/5 as my common ratio. So what's 3/5 of x? 3/5 of x would be, oh, well, 3/5 of that term is this term. So it's 6/5. And 3/5 of this term should be this term, 18 over 25. And 3/5 of that term, and so on and so forth, they're all going to match up. So all the terms match up except for the first one. So when I subtract these two things, those cancel, everything on down the line is going to cancel. I'm left with that first term 2 on the left-hand side of my equation. And on the right-hand side, I have x minus 3/5 x, so that's just 2/5 of x. Well, if 2/5 of x is 2, I can multiply by 5 and divide by 2. I will get that 5 equals x. If I were to add an infinite number of these things together, I would get extremely close to, and once I hit an infinite number, I'd get to 5. Let me pause for a second and we will see that in a spreadsheet. Okay, so what I've done on this left-hand column, this one in column A, is I said, oh, well, let's just set this to 2. And this one I set, if you can see up there in my formula bar, it's a little small, 0.4 or 2/5 of 2, and this is 2/5 of that and 2/5 of that, etc. What I've got going on over here is this is just equal to that, and this is equal to whatever's above it plus whatever's to the right. So I'm going to copy this and I'm going to paste it a few down here. And we're up in the 3s, and let me Control C and go down a couple more and Control V. And we're down in the 3.33, and it looks like someone, presumably me, made a mistake here. Oh my. Let me pause and ponder what happened. And that was pretty easy. I multiplied by 0.4 instead of 0.6. I was looking at my sheet over here and saw the 2/5 multiplied by 2/5 instead of 3/5. So now when I get 3/5 of 2, I have a 1.2, 3/5 of that, 3/5 of that. Sorry about that. When I add these things up, you will see that after a couple of iterations, they're already reasonably close to that goal of 5. If I scroll down and I only put in 100 or so of the ones in the left column, but if I scroll down, we're getting really close to 5. And at some point for the computer's rounding, it is indistinguishable before we even get to 33 of these things. Okay, nice. Moving on. Okay, so find the S of n of the sum of the first n of these. Okay, so now specifically, I'm going to go to this equation over here, and it's an equation which we could derive by doing this stuff. But I'm going to plug in that first term, which is really 2/3 times 4, so 8/3 is my first term. It's not written the way that we're used to see it with an n minus 1 over there, which is fine. And I'm going to multiply by 1 minus that common ratio, which is 4 to the n over that 1 minus 4. 1 minus 4. Okay, and that is about as good as it gets. We can simplify this, not knowing exactly what n is. 1 minus 4 is obviously -3. I get -8/9 times 1 minus 4 to the nth. Okay. Same thing over here and over here. This one, of course, is in sigma notation. I'm going to pause and do these. Give you guys a chance to pause and do them as well. Okay, so here is that part C1. I did it out, and let me walk you through what's going on here. In column A, I simply have the integers 1, 2, 3 telling me what step I am on. In column B, I have the value of a sub n, and in volume C, it's just recursively adding up these things. In D, on the other hand, I don't have the recursive formula. I don't know if you can see in my formula bar there. It says 0.75, which is 3/4, 1 minus, and that power thing really tells me that I'm going to take the first number in the argument and take it to the power of the second one. So I'm taking -3 to the power of whatever's in that A1 column. And if I scroll down one, it'll be in that A2 column that I'm taking the second power this time, the third power, and so far. And seeing that those match up perfectly, it looks like it all works. Let me turn this off and go back to a larger view of these. And so you can see here it is a little bit unsimplified. There's that 3/4 times 1 minus -3 to the nth. Okay. Same treatment over here. I didn't do it in Excel, but there it is. Okay. Hopefully you've got something similar to that. Okay. Just to be clear, when I say a sequence, I'm talking about the list of terms. When I say a series, I'm looking at the sum of those terms. So a sequence, there really isn't an answer. There are a number of answers, one for every term, and a series is the sum of those. So we started off with that infinite sum, and now we're going to come back around to it. But remember that a finite sum is really just an infinite sum minus another infinite sum. So if I wanted to know the sum from 1 to 100, I could do the sum from 1 to infinity minus the sum from 101 to infinity. I don't know, just a way of thinking of it. All right, an infinite sum of the form this, which goes on forever with the first term a sub 1 and a common ratio r, is called an infinite geometric series. It is denoted by this thing. We can solve for them as long as r is less than 1. If r is larger than 1, then each subsequent term gets larger than the previous one and larger than the previous one, and it's just never going to end. After a few iterations, you could end up with something which is huge and only getting huger. It's not going to approximate something. This does remarkably have some practical purposes. There are a couple of examples we could run through. One which I always like to think about is back in the day, there were two competing audio video stores. There was Good Guys and there was Circuit City, and they were right across the street from one another in a few different towns. Like in Glendale, they had two stores right across from one another, and both of them said that they would always beat one another's advertised prices, and that was kind of the trick, advertised prices by 10%. So if there were a $150 stereo and the which was being advertised at Circuit City for $150, then you could and Good Guys had it for $100. Well, Circuit City was more expensive, so go there. They would beat that advertised price by 10%. And then you could go back across the street to the other one and beat it by 10%, and beat it by 10%, and beat it by 10%, and walk back and forth. And if you did this an infinite number of times, the stereo wouldn't be free. There would be a finite amount of savings that you could actually earn. So there's one possibility. Another possibility, and I used to do this in my physics classes when I taught physics, was I would bring in a whole bunch of CD cases. And yes, people still listen to CDs. Where are you, Alex Lee? There's someone. People still listen to CDs. And I would bring in CD cases, like hundreds of them, because I own lots and lots of CDs. And we would work on stacking them and trying to get the top one the furthest amount over. Could you get it so that it was entirely not over, I should say, the bottom CD, and a little bit of math, a little bit of physics, and a lot of this stuff we learned that we could. Anyway, convergence or divergence of geometric series, if the finite sum S sub n approaches a number L as n goes to infinity. So if we take an infinite number of steps and we get to a specific number, that number we're calling L, we say the infinite series converges. So that first example we saw on the other page, it was convergent. We call L the sum of the infinite geometric series, and we write that L equals the sum of the geometric series. Okay, that was pretty easy. If the series does not converge, it is said to diverge. Let's explore when a geometric series might converge, although I feel like I have already given this one away. So they're writing this, and I claimed that R had to be less than 1. I guess I could be a little bit more specific about that, so I guess I haven't given it entirely away. There is a little addition to that, which we might add. And there it is. Not so much that R has to be less than 1, but the absolute value of R must be less than 1. So really, R can be anything from -1 to +1. It can't be -2. And the infinite series will converge, and its sum is given by this simplification of that previous one. And again, this is what I get when I do that technique that I did at the beginning, where I set that series equal to something. I then below it write whatever R times that sequence was, subtract off all the terms, and then divide by, not the reciprocal, but 1 minus that R. So I think we had 3/5, and so I divided off by 2/5. Determine if this sequence converges or diverges. Well, right off the bat, 2/5 is less than 1, or the absolute value of 2/5 is less than 1. So it does. If it converges, find its sum. I am going to do it my way here, where I'm going to say, oh, my first term is 3. My next term is 2/5 of 3. I don't really care what that is. My next term is 2/5 squared times 3 and plus ... I don't know what it is, so I'll call it x. This time I'm going to write the x on the left-hand side. But if I look at what 2/5 of x is, well, 2/5 of that term is this term. And 2/5 of this term is this term. And those should repeat one another forever. So I should end up, if I subtract, with 3/5 of x, which equals 3. Let's multiply by 5/3, and I'll get again that x equals 5. Okay. An example of this that we've probably seen in most of my classes this year is that 0.9 repeated is equal to 1. Let's show that 0.3 repeated is equal to 1/3. So what I'm really doing is I'm going to say that this is 0.3 is a sub 1, and a sub n is equal to my a sub n minus 1 times 1/10. Let me get that so we can see it. Okay, so really if I were going to add all these, I'd be adding 3 to 1/10 of 0.3, which is 0.03, and I'd be adding that to 1/10 of 0.03, which is 0.003, and so on. So I'm going to use their formula this time, and I'm going to say that the sum, I'm not going to write all the little stuff about it, but the sum is my first term, which is 0.3 over 1 minus, and that common ratio was 1/10. 1/10. I'm going to say that it's equal to 0.3 over 0.9. Oh, I don't need those points. That is equal to 3 over 9. Oh, that reduces. That is equal to 1/3, at which point I get to say, ta-da. Determine if the geometric series converges or diverges, to which I say, it diverges. 5/3 bigger than 1. If I try to do this, it's just not really going to go anywhere. Okay, we are not going to do these annuity problems. You are more than welcome to look it up and run with it yourself. It is something neat, but that is where we are really going to call it. Okay. Thank you so much. Have a good one.